Dublin Metro North is a planned light rail high-capacity system for Dublin that will link St Stephen's Green in the city centre with the airport and will end north of Swords. The metro will be through single-track, twin-board tunnels at road level and elevated on a viaduct over the M50 motorway. The distance between Dublin City Centre and the airport is 15 kilometres. The journey time will be 19 minutes. The estimated cost is €2.4 billion. This short film shows typical construction methods that were used to construct similar light rail systems. It is useful to see 3D visualizations and animations so the site team, emergency services, stakeholders and the public can get an understanding of the construction process and timeline. Tunnelling. The twin-board tunnels will be 5.8 metres internal diameter, with a track separation of 18 metres. A tunnel boring machine, also known as a TBM, is used to excavate and place the concrete precast curved tunnel wall segments that form tunnel rings. The tunnel boring machine pushes itself forward by jacking off the placed wall segments as the head rotates and digs the tunnel. The tunnel boring machine is delivered in sections and is lowered into the underground launch station or shaft from where the tunnelling starts. The tunnel precast concrete segments are delivered by road and lowered into the underground station and carted through the tunnel under construction to the back of the tunnel boring machine. The excavated material is transported by conveyor belt from the tunnel boring machine to an underground station or shaft, from where it is lifted to ground level and loaded onto trucks for disposal off-site. Twin-board tunnels with cross passages for emergency evacuation is the design. Tunnels will be in rock to avoid ground loss and settlement under building foundations and roads. TBM progress will be staggered in the leading and trailing tunnels. The TBM will walk through stations that are excavated in advance. Tunnel boring machine breaking through into the excavation for a station, which confirms the accuracy of the setting out and survey work, to the relief of the site team. After tunnelling, the tunnel fit-out takes place, where tracks are installed along with the electrical power, drainage and ventilation systems. The sleepers and rails are transported into the tunnel using a gantry crane on wheels. A concrete train that batches and pumps concrete places concrete under the sleepers to form the floor slab. A drilling machine that runs on the installed tracks drills the tunnel wall for brackets that will support the surfaces. Shown are the moulds used to cast the tunnel wall segments. The process to cast a concrete tunnel curved wall segment is: clean and coat the mould with release agent, place the reinforcement cage in the mould and close the top shutters. Pour concrete into the mould and vibrate. Remove the concrete segment from the mould after it has hardened and transport to storage. Contractors' temporary site facilities. Reinforcement cutting and bending operation. Cutting and bending is carried out on three-phase electrically driven machines operated manually. The bars to be cut are placed on benches where they are marked and fed manually into the shearing machine. Bars to be bent are hand bent using a bar bending machine with formers. Following cutting and bending, bars of similar size and shape are grouped and tied together with an identification tag. quarry. Rock is extracted by drilling and blasting. Blasting is used to loosen and fragment the rock so the rock fits into the jaws of the primary crusher at the crushing and screening plant yard. Grizzly screen used to separate the rock from the fines and dust produced by the blasting. Using a series of crushers and screens connected by conveyor belts, different size ranges of aggregates are produced and then transported to the concrete batching yard. Multiple deck screens separate the aggregates into different size ranges, for example 25 to 19 mm, 19 to 12 mm and 12 to 4 mm. Jaw crushers are used to reduce the rock size to a maximum of 100 mm. Cone crushers are used for secondary crushing to produce cube-shaped aggregates for concrete and pavement asphalt. This chart shows details and outputs of quarry crushers and grizzly screens. The production equipment shown has an output of 130 cubic meters per hour. Concrete batching yard comprises pan-type concrete mixer, control cabin, silos for cement and fly ash, aggregate bins and conveyor belt system to feed the mixer, also aggregate storage bays and water storage tanks. The mixing is computer controlled and has a dynamic screen display showing the process. Wheel loaders fill the inline aggregate bins. The aggregates drop onto a weighing conveyor belt that transports the aggregates to a skip. The skip travels up an elevator and discharges into the mixer along with water and cement. The concrete mixer homogeneously combines cement, aggregates, water and admixtures to form concrete. The discharge door on the bottom of the pan rotates to open. In hot climates, flake ice is used to cool the concrete mix. Table shows the equipment details and hourly production outputs for different types of concrete mixes. Laboratory for testing the aggregates and concrete for compliance with the specification. Placing concrete. Concrete is delivered to the workplace by truck mixers. Concrete pumps are used to place the concrete, and the concrete is compacted using internal vibrating pokers. The concrete is raked and levelled with a straight timber, initially tamping the surface, then using a back and forth motion while moving across the surface. The surface is finished using rotating power floats that give a smooth, dense and even finish. Underground stations. Construction method for underground metro stations with diaphragm walls. The outline construction sequence is: divert roads, footpaths and underground and overhead utilities outside the area of the proposed site. Erect hoarding and gates to make the site secure. Construct diaphragm walls to form the station box. Excavate ramp for tipper trucks to use to haul away excavated material from within the box. Excavate to formation level. Construct floors and roof slabs. Fit ticket booths and ticket barriers. Install lifts and escalators. Complete finishes, electricals, etc. The construction sequence for the diaphragm wall is: excavate and construct guide-reinforced concrete walls to ensure correct alignment of the proposed diaphragm walls. Excavate panels 6 metres long. Keep 12 metres from other excavated or freshly poured panels. Using crane with suspended hydraulic grab or cutter with steering mechanism to ensure verticality. Bentonite, which is a mixture of water and a special clay, is used to support the excavation. Insert steel stop ends with water bar. The stop end will be removed during excavation of the adjoining panel. Place prefabricated reinforcement cage in the excavated panel. Concrete the excavated panel with the placed reinforcement cage using 2 tremie pipes with hoppers to prevent the cement washing out of the concrete during pouring. Ground conditions. Subsurface geology along the tunnel routes. Shown is a 3D model of the bedrock surface under Dublin City. The limestone bedrock is between 5 and 25 metres below ground level. The overlying deposits are generally boulder clay with thin layers of sand and gravel. The water table is between 2 and 4 metres below ground level. The bedrock geology map of Ireland gives the rock as limestone and mudstone along the tunnel route. Following are examples of exposed rock showing the layer structure. Cliffs of Moher are formed of layers of siltstone, shale and sandstone. Dún Quinn Pier lies at the western tip of the Dingle Peninsula. Motorway cut through limestone rock. Dublin Pier limestone pavements with crisscrossing cracks. Skellig Michael's sandstone rock is greatly weathered. The excavability of rock depends mainly on the rock strength and the layer thickness. This diagram shows excavation methods for rock of various strengths and thicknesses with a free face. The sequence to construct an underground station 24 metres deep where the bedrock is 10 metres below ground level. Construct diaphragm walls down to bedrock. Excavate and cart away the clay. Install temporary struts. Excavate rock to final level and cart away. Install rock anchors and grout the vertical face of rock excavation if necessary. Tunnel in and out of the excavation. Construct station box. Remove temporary struts and backfill between station box and diaphragm walls. This clip shows the excavation for an underground station that is mostly in rock. A secant pile wall with ground anchors holds back the clay over the rock. Methods to excavate rock in tunnels and underground chambers are: road headers are powerful rock-cutting machines designed to excavate tunnels and underground chambers without using explosives. Drill and blast rock to loosen and fragment, then load and cart away. Using excavator with hydraulic breaker to excavate rock. Excavator with a rotary drum cutter used to excavate rock and shape the tunnel to profile. The rock shield is a mobile elevating work platform with a canopy incorporating a shock absorption system that is designed to protect the worker from the impact of a rockfall when removing loose rock from the tunnel roof. A rock cable bolt is a long anchor bolt that is grouted in a drilled hole for stabilizing rock excavations. It ties the unstable surface rock back into the solid rock mass. Sprayed concrete lining involves spraying the excavated ground with concrete to stabilize the surface and form the permanent tunnel lining. Is used for the station platform tunnels and cross passages. Viaduct. Viaduct over the M50 motorway. 3D animation showing construction of a metro viaduct. The viaduct is constructed using the span-by-span method with an overhead launching gantry to lift and place the precast U-shaped segments. The viaduct segments are post-tensioned together to form the spans. The concrete segments are manufactured using the short line match casting methods. Where sequential segments are poured against the previous cast segment, this ensures that the segments will fit perfectly on site. Photographs showing a precast yard for the manufacture of viaduct segments. This clip shows a launching gantry that moves itself forward and lifts and places the precast concrete segments that form the viaduct spans. The segments are stretched together with steel cables that are threaded through the ducts in the segments. The cables are stretched and locked at the end anchors, after which the ducts are filled with grout. Straddle carriers used to move and lift precast deck. Post-tensioning and in-situ bridge deck. Ducts and the bearing plate trumpets, also known as anchor cones, are fixed in place prior to concreting the bridge deck. The strand coil is placed in the reel trolley. The pushing machine is positioned in front of the anchorage and the duct into which the strand is to be threaded. A steel circular block and wedges are fitted to the strands at the anchorages. The stressing starts after the concrete reaches its design compressive strength. 2 multi-strand stressing jacks with a capacity of 600 tons pulling force and hydraulic pumps with pressure gauges are used. The tensioning requires the simultaneous reading of pressure and cable elongation and checking the comparison between these values and the theoretical ones. After stressing, the ducts are grouted. Shown is the construction sequence with a timeline and photographs of the activities for a 3-span bridge with an in-situ concrete post-tensioned deck where the ground around the abutments had to be surcharged. A self-propelled modular transporter, SPMT, is a self-loading platform with many wheels that is used for transporting objects such as large footbridge sections. Each wheel can swivel independently from the others to allow it to turn, move sideways or spin in place. Piling. Piles are used to transfer the load of a heavy structure such as piers to a viaduct deep into the ground. Shown is the plant and equipment used to construct in-situ concrete piles. The sequence to construct a pile is: drive a temporary steel tube known as a casing into the ground using a tracked crane with a suspended hydraulic piling hammer. Bore out the ground inside the casing with a piling rig. Place a prefabricated reinforcement cage into the bored hole. Pour concrete into the bored hole using a concrete pump with a tremie pipe suspended from a crane. Extract the temporary casing. Load test a pile. Other pile testing methods are echo testing, ultrasonic testing. A hydraulic pile breaker suspended from an excavator is used to break away the concrete and leave the reinforcement exposed at the top of the pile. Program. Shown is an example of a visualization of a construction program for the tunnelling, underground stations and the cut and cover sections of the metro. Included are the route, longitudinal section, locations of stations, and a timeline. The TBM will progress at a rate of 20 metres per day depending on ground conditions. Assembly of the TBM in the launch shaft or station takes a few months. Road construction. Roads in the vicinity of stations and where the metro will be at ground level will have to be diverted and reconstructed. 3D animation showing the construction sequence, methods and plant to construct a road. Asphalt batching yard is composed of cold aggregates feed bins, aggregate drum dryer, bitumen heated storage tanks, batch tower for mixing the hot bitumen and hot aggregates, storage bin for hot mixed asphalt, control room, offices, laboratory, weighbridge and diesel tanks. The mixing is computer controlled and has a dynamic screen display showing the process. Aggregates are placed in individual cold feed bins. Aggregates are fed onto the conveyor belt under the bins and are transported to the drum dryer. In the rotating drum dryer, the aggregate is heated and dried as it tumbles through the flames. The hot aggregate is transported to the top of the plant mixing tower by a bucket elevator. Upon discharge from the elevator, the hot aggregate passes through a set of vibrating screens into one of the hot storage bins. The hot aggregate is weighed and emptied into the twin-shaft pug mill mixer and the hot bitumen is added. Asphalt laydown and compaction operation. The asphalt paving process uses paving machines on tracks, tipper trucks, compaction rollers, string lines and matching shoes for level. To start, the paver is positioned and its screed is extended and lowered onto timber blocks set at the required level. Tipper trucks unload hot asphalt into the paver's hopper. The paver will spread the asphalt. Rollers will compact and finish the asphalt to a smooth and even surface. The asphalt has to be hot to achieve compaction. Field testing for level, smoothness, texture and skid resistance. laboratory for testing bitumen, asphalt mix, compaction and rutting. Traffic management will be necessary to divert vehicular and pedestrian traffic away from the works. The associated inconveniences and disruptions with the project will be kept to a minimum, and the stakeholders and public will be kept informed of developments. Earthworks include excavations, trenching, haulage, backfilling, filling and compaction. Shown are loading shovels, excavators, rock breakers, dozers, graders, tipper trucks, rollers and a road milling machine at work. Excavations can be classified by the type of material, for example topsoil, earth, rock. Alternatively, may be classified by their purpose, for example stripping, roads, foundations, structures, underground, dredge, trenching. Metro North is a major project that will provide Dublin with an integrated public mass transit network. Trains will be 60 metres long, running up to every 2 minutes at peak times. The capacity will be 17,000 passengers per hour per direction. Ridership is estimated at 30 million passengers per year. Metro North will reduce traffic congestion, air pollution and road accidents. 3D visualisation and animations of the construction process is beneficial to the site team, client and stakeholders to understand how works will proceed and when. The use and implementation of 3D visualisation results in increased productivity, fewer mistakes, less waste and lower costs. 3D visualisations are ideal for capturing and sharing know-how. In construction, knowing what has to be done is easy, knowing how to do it and getting it done is the hard part. Using 3D images in films, infographics and presentations to show proposed construction methodologies, the required plant and sequence is innovative and has many advantages when it comes to planning, organising and communicating to the client, site team and stakeholders. Regarding health, safety and environmental issues, all risks will be assessed and control measures will be implemented to eliminate or minimise the potential likelihood of personal injury, damage to buildings, damage to the environment and traffic accidents. Demonstration showing space required by 200 commuters in 177 cars, without cars, on bikes, on 3 buses, on 1 light rail train. Shown is the route of Metro North and the locations of stations between St. Stephen's Green and the airport. For similar educational construction films on airports, seaports, motorways, pipelines, oil and gas plants, see my YouTube channel. The films include the construction sequence, plant, equipment and methodologies.